dear students, in the previous video, that was video number 8, I explained the proof of if two functions are integrable, suppose f and g are integrable, then f by g is also integrable. In previous videos, we have studied algebra of integrable functions. If f and g are both bounded and integrable, then f plus g is integrable, f minus g is integrable, f into g is integrable, f by g is also integrable. Now, next theorem is, if f is bounded and integrable in a closed interval AB, then mod f is also bounded and integrable in AB. But converse of this is not true. What is the converse? If mod f is bounded and integrable in AB, then f is also bounded and integrable in AB. It is not always true. First we prove this theorem, and to prove that converse is not true, we take one example. Now how to prove this one? First thing is you have to prove that mod f is bounded. Second thing is mod f is integrable. Now what is given? Since f is bounded in AB, for all x belongs to AB, there exists k, so that mod fx is less than or equal to k. There exists k, which is positive integer, k positive integer, so that mod fx is less than k. This implies mod fx is also bounded. This is the first part. Second, to prove that it is integrable, we use sufficient conditions for integrability. Since what is given here, f is integrable, there exists a division d is equal to x0, x1, x2, so on, xr minus 1, xr, xn minus 1, xn is equal to b, whose norm is less than or equal to delta, such that the oscillatory sum of f is less than epsilon. Oscillatory sum of f due to that division d is less than epsilon. This is important because it is given f is integrable. Now we have to prove that mod f is also integrable. For that, let capital MR dash MR dash and capital MR MR be the bounds of f and mod f in the delta. What is delta? R subinterval. Delta R is R subinterval. Also, let alpha 1, alpha 2 belongs to delta xr minus 1, xr. Then we have one lemma here. What is the lemma? The oscillation of a bounded function is supremum of the set of numbers f of alpha minus f of beta. Oscillation of a bounded function. What is the oscillation? M minus m is the supremum of this set. What are alpha beta? Belongs to A. Now we have taken alpha 1, alpha 2 belongs to delta. Therefore, we have than or equal to mr minus mr. Correct? mr minus mr. But by inequality of absolute values, we have mod f of alpha 1 minus mod f of alpha 2 is less than or equal to mod f of alpha 1 minus f of alpha 2. 1 minute. Mod a minus b is greater than or equal to mod of mod a minus mod b. Correct? Mod a minus b is greater than or equal to mod of mod a minus mod b. Now here, what are the bounds of mod f of alpha 1 minus f of alpha 2? They are mr minus mr. 1 minute. I go to this step. Mod f of alpha 1 minus f of alpha 2 less than or equal to mr dash, because mr dash are bounds of f. Therefore, we have by lemma capital mr dash minus mr dash is greater than or equal to this. Now, therefore, we have mr dash minus mr dash. What is this? mr minus mr. We have used lemma here. This lemma. Therefore, sigma mr minus mr delta is less than or equal to sigma mr dash minus mr dash. Mr dash minus mr dash. But what is given? It is given this fx is bounded. Fx is integrable. Fx is integrable in AB. Therefore, oscillatory sum of f in AB is less than epsilon. What is the oscillatory sum of f in AB? Oscillatory sum of f in AB is sigma mr dash minus mr dash. It is less than epsilon. I think I have taken same thing here. Mr dash minus mr dash is the oscillatory sum of f in AB. It is less than epsilon. Therefore, sigma mr minus mr delta is less than epsilon. Now, what is this? It is the oscillatory sum of mod f. Therefore, oscillatory sum of mod f in AB is less than epsilon. There exists a division of mod f such that the oscillatory sum of mod f is less than epsilon. This implies mod f is also integrable. Now, converse of this is not true. Converse of this is not true. Converse of which is not true. Above theorem is not true. For that, consider the example. Consider the following example. We take Dirichlet's function. Let fx is equal to 1 when x is 1 minute. Fx is 1 when x is rational. Minus 1 when x is irrational. This is called Dirichlet's function. Now this function here mod f is integrable, but f is not integrable here. F is not integrable. Mod f is integrable, f is not integrable. Because what is mod f? Mod f is 1 here. Because if you take mod, it becomes 1. For all x belongs to AB, we consider AB as any closed interval, which is constant. Which is constant. Every constant function is integrable. We have already proved. Every constant function is integrable. Is integrable. Therefore, mod f is integrable. Mod f is integrable. But fx is not integrable. For that, we consider upper and lower integrals. Let d is equal to x0, x1, etc., xr minus 1, xr, xn minus 1, xn. This is equal to b. B, any division of AB. We verify whether f is integrable, or in fact we prove that f is not integrable. For that, we consider upper and lower integrals. Now, mr, small mr, be the bounds of f in delta. F in delta. What is delta? xr minus 1 xr. This is delta. Then what is a to b bar fx dx? A to b bar fx dx, upper integral is infimum of capital S. What is capital S? Where capital S is sigma capital mr delta r is equal to 1 to n. It is sigma r is equal to 1 to n. What is capital mr? Capital mr is 1 into delta, because capital mr is the upper bound, small mr is the lower bound. And what are the functional values of fx? 1 or minus 1 in any interval. Sub-interval also it is 1 and minus 1. So it is b minus a, because sigma delta r is sum of the length of the interval. It is this b minus a. So what is upper integral? It is infimum of this a, b minus a. So it is b minus a. Upper integral is b minus a. And what is the lower integral? A bar to b fx dx. A bar to b fx dx is, it is the supremum of small s. Supremum of small s. What is small s? Small s is sigma 1 to n small mr delta. From the beginning only we have studied this. What is capital S and small s? Small s is therefore sigma r is equal to 1 to n. Small mr is minus 1 into delta. So it is minus of sigma r is equal to 1 to n delta. So it is minus of b minus a. So it is supremum of minus of b minus a. This set, it is constant, it is minus of b minus a. So it is minus of b minus c. Now here, this is upper integral, lower integral. They are not equal. Since a to b bar fx dx is not equal to a bar to b fx dx, fx is not integrable. Fx is not integrable. Therefore, mod f is integrable, but fx is not integrable. Fx is not integrable. Next, we consider some problems on this topic. Some problems. First example is like this. Consider the example. A function fx is defined by fx is 1 upon 2 raised to n if 1 upon 2 raised to n plus 1 less than x less than or equal to 1 upon 2 raised to n. What are the values of n? 0, 1, 2, etc. And f of 0 is 0. Show that fx is integrable. Also evaluate 0 to 1 f of x dx. First part is we prove that fx is integrable. For that we can use any property of integrable functions. Now see the definition of fx. I reach the values of fx, how it is defined. When n is 0, you will get fx is 1 if 1 upon 2 less than x less than or equal to 1. Fx is half if 1 upon 2 square less than x less than or equal to 1 upon 2. And it is 1 upon 2 square if 1 upon 2 cube less than x less than or equal to 1 upon 2 square. You know how to write the value of fx. Take n is 0 first, then 1, then 2 and so on. And finally 1 upon 2 raised to n if 1 upon 2 raised to n plus 1 less than x less than or equal to 1 upon 2 raised to n. This is fx. Now fx is discontinuous set. What are the points of discontinuities here? It is discontinuous set 1 by 2, 1 by 2 square, 1 by 2 cube, 1 by 2 raised to n. At all these points, it is discontinuous. 1 by 2, 1 by 2 square, 1 upon 2 cube, etc. It is discontinuous. But what are the points of discontinuities? There are infinitely many discontinuities. But these points of discontinuity or set of points of discontinuity has a finite limit point. Finite limit point. Therefore, fx is integrable. So we have proved this theorem. If fx has infinite discontinuities, but the set of points of discontinuity has finite number of limit points, then it is integrable. Using that property, it is integrable. Or one more property you can use. See here, values of x increases in this order. 1 by 2 cube, 1 by 2 square, 1 by 2, 1 by 2, 1. When x increases, fx also increases. So fx is monotonically increasing, hence it is integrable. Or we can use this one. So first part is fx is integrable. Now second part is to find 0 to 1 fx dx. We have 0 to 1 fx dx is, it is limit n tends to infinity, integral 1 upon 2 raised to n, n plus 1 to 1 upon 2 raised to n fx dx. N tends to infinity. This is This can be written as, it is integral, or I write limit n tends to infinity, limit n tends to infinity, integral 1 by, what is the first one? 1 by 2 to 1 fx dx plus 1 by 2 square to 1 by 2 fx dx, 1 by 2 cube to 1 by 2 square fx dx, plus so on, plus so on. Now how it is defined? Say we have listed values of fx. Limit n tends to infinity of 1 by 2 to 1. In 1 by 2 to 1, how it is defined? 1 it is. Plus 1 by 2 square to 1 by 2, it is 1 by 2. 1 by 2 cube to 1 by 2 cube to 1 by 2 square, it is 1 by 2 square, and so on. Therefore, it is limit n tends to infinity. What is integration of 1 dx? X. Therefore, x from 1 by 2 to 1 plus 1 by 2 into x value from 1 by 2 square to half plus 1 by 2 square integration 1 by 2 square take common, 1 by 2 square common, 1 dx remains, integration of 1 dx is x, 1 by 2 cube to 1 by 2 square plus so on. Now this is limit n tends to infinity 1 minus half plus 1 by 2 into 1 by 2 minus 1 by 2 square plus 1 by 2 square into 1 by 2 square minus 1 by 2 cube, and so on. So it is limit n tends to infinity 1 minus half 1 by 2 square minus 1 by 2 cube plus 1 upon 2 raised to 4